So welcome everybody to an Allocator as a handle to a heap. I'm Arthur O'Dwyer. This is one of 3 talks that I'm giving this week, and you should all come to all of them. In fact, this is the one you can walk out of because you can already see it online. I gave it at C++ Now earlier this year in Aspen, and there it had a 90-minute slot. Here it has a 60-minute slot. So I don't know how far we're going to get. Maybe we're going to get all the way, maybe we're not. We'll get farther if you don't ask questions, but it's already been recorded once, so the stakes are very low. If you have a question, please do ask it. Please do raise your hands, ask questions, whatever. And I reserve the right to steamroll over any questions that are leading us in an unproductive direction based on where my slides want to take us. But basically, yeah, you're getting the second draft. It's already been recorded once. So, Allocator is a handle to a heap. Why do I say this? Let's start at the beginning. First we even have an outline. Yeah, we're going to be talking about this. We're going to start at the beginning. We're going to talk about what are objects, what are values, and I'm going to tell you what is an allocator, what is a memory resource. We're going to talk a little bit about what I call copy-only types. We're going to talk about rebindable families. We're going to talk about what else is in the C++ allocator model besides being a handle to a memory resource. And then we're going to relate allocators to other parts of C++. So, objects and values. C++, it's a multi-paradigm language, but part of that is it's an object-oriented language. What is an object? For that matter, we've talked about value semantics. What is a value? Well, I generally try to divide objects into 2 categories, a dichotomy between object types and value types. Any type that you make should be one or the other, and not parts of both. You know, a value is something like int. I think Scott Myers often says, "Do as the ints do. Be like an int." Ints are copyable. They're comparable. You can pass them around. They're copies are interchangeable. That's a value. Value semantics. Object types are more classical object-oriented. They may be polymorphic. They're generally identified by their address. And if I have 2 objects at different addresses, generally they're not interchangeable. And the reason they're not interchangeable is because they have state. I'm mutating an object. The interesting thing about objects is I said an object has an address. You can have a pointer to an object. You can name an object with its address. It has some sort of unique identifier or handle. These are all interchangeable terms. And that handle, that address, that pointer, is itself a value type. So the name of an object is itself a value. I have the value, the pointer value, ampersand a. That I can pass around a pointer. Copies of pointers are interchangeable. Pointer is a value type, but the object itself, not necessarily. Now, in this case, the object itself is an int, and I just told you that int was a value type. This is where it gets confusing for me. That a C++ object is in part defined by its in-memory representation. Even these things that we want to think of as value types. You know, an int has the value 42, but it also has a memory address because we're in C++. And so I can take its address, and maybe there are some ways in which 2 ints at different addresses may not be substitutable for each other. Vice versa, I can think about having object A of type int, and I can think that it, in some sense, not only has a state which I can mutate. You know, I can plus equals to an int to increase or decrease the value that it has, and I'm mutating its state by doing that, but also in some sense changing its value. And this gets very confusing if you let it, or if I make it so. So just know that this dichotomy does break down as you go lower into the sort of quantum levels of C++. But at the very high level, distinguishing between value types and object types, I think is important. And speaking of which, there is another talk on this subject. Juan Pedro Bolivar Puente is giving his talk, Most Valuable Values, this Friday at 1:30. So if you want to hear more about that, go there. Where are we going here? Oh yeah, something else I wanted to say about this slide. Two interesting things going on this slide with our A and our B. Number one, that we have this int that I'm calling an object, right, which we already kind of covered that. But also that these two objects, A and B, have different C++ types. Right? One is an int and one is a long. But in some sense, they have the same Platonic value, 42, which is represented by the value 42 in that little cloud. That there's this Platonic ideal of 42, that both of these concrete objects, in some sense, represent that value. But they do it with different bit patterns, right? And if there was a double, that would be another kind of bit pattern, all representing this idea of 42. So there's some sense in which the value is distinct as well from the object representation. And there we're just talking about integers. Let's talk about containers. What is a sequence container, like a vector or a list? On the one hand, a container behaves like a value. If I have a vector of 3 ints, I can make a copy of it, and that copied vector will compare equal. It will have all the same properties as the original. I can pass vectors around by value, return them by value. They behave a lot like values. But at the same time, they have these details of their object representation that are very important to us as C++ programmers. The container is an object that holds and manages elements, which themselves are objects. So on the right-hand side here, on the left, we have the Platonic ideals of clouds and whatnot. Platonic ideal looks a lot like Python. That's completely coincidental, I promise. And on the right-hand side, we have the more C++ view of the world, where these are all objects, and they have some sort of memory layout. And we have these mysterious symbols. We have these boxes. We have two sets of boxes. And maybe we know that the left-hand box there, the object v of type vector int, that's probably allocated on the stack. But then we have these other two boxes. Where did they come from? They're in memory somewhere. Where did we allocate that memory from? And then this thing that looks like an arrow, a little box and arrow, what is that exactly? These are the questions that we have, and the answers are provided by the C++ allocator model. Where does the memory for these things come from? What is that thing that looks like a pointer? So std vector, the standard vector type from the STL, is parameterized not only on T, but also on an allocator type A. That parameter gets a default, which is why you don't usually see it in your code. But if you're here, it's probably because you're aware that allocators exist. If not, spoiler alert, allocators exist. So the allocator answers these questions. Where does the memory for v sub I come from? It comes from a call to the allocator, to its allocate method. And what is the thing represented by the box and the arrow? It's an object of type pointer, the member type def pointer that the allocator has, and we'll cover that more in several slides from now. The container holds an instance of the allocator type A within itself. So a container has an allocator, and anything that can be funneled through that instance is funneled through the instance. So anytime the container does an allocation, it's going to ask the allocator, hey allocator, it's time for me to allocate some stuff. How do I do it? It's time for me to deallocate some stuff. How do I do it? It's time for me to have a pointer to some stuff. What is the object representation of that pointer? Things like that. And so it holds that instance of the allocator type within itself. What kind of state or what kind of innards can that allocator instance have? Well, prior to C++17, the only standard allocator type that existed was called standard allocator, and it was stateless. It was an empty class type. It had no state at all. It would typically be optimized away through the empty base optimization. And so when people start experimenting with allocators and more fancy allocation strategies, they start realizing that it would actually be nice to have some data inside an allocator, some state that it could carry around. And they didn't have any guidance for how to do this because the only allocator type up to 14 was stateless. There was no guidance either in the standard document or in standard libraries as to how do you make a stateful allocator in the first place. And this would lead to people trying to implement stateful allocators something like this. This is something that at least up to a year ago, maybe fixed as of C++ now, but I bet someone's going to come up to me in the hall this week and say, I'm trying to do something like this. Right? I want to make an allocator, which I'm here calling bad. It's templated on T, and it has a sort of buffer, a big buffer inside itself, and it has this allocate method that's just going to bump the pointer, and I can make a std vector of T, comma this allocator, and then it will have the buffer inside the vector itself. It'll be like I had a fixed capacity vector, right? The vector and the buffer right next to each other, and this is going to be great. And then they go to try to make a copy of the vector, and all the pointers are pointing into the old guy, and it just doesn't work. Bryce?
Is it the object that's stateless rather than the thing the object points at?
Yes, we're going to get to that. Bryce, real fast. Why align as 16? Yeah, why not? Yeah. Maybe they shouldn't even do this. They are really bad at programming, as we can say. So yeah. So in 17, we got this thing called polymorphic allocator. Std PMR, polymorphic allocator, where PMR stands for polymorphic memory resource. Yeah, I don't know. Nested namespace is considered bad. But we have this thing called polymorphic allocator. And it is, we'll see it in about slide 16, we'll see the actual code. But polymorphic allocator is basically a pointer to a std PMR memory resource. You take all that shared state, the big buffer that we had before. In fact, this is almost exactly struct bad, right? It's just we've changed its name. We're not calling it struct bad anymore, so you can tell it's okay. But we're not going to call it an allocator. We're going to have a new name for it. We're going to call it a memory resource. And it's going to be an object type. That means it has an inheritance relationship with something. It also has virtual methods and stuff, although you don't see them here. And it lives at a specific place in memory, right? That specific place is where this big buffer data is going to live from now on. We have 1K of memory allocated somewhere specific. We're going to have pointers all over the place, maybe pointing into it to allocated objects. So it's important that it not move around. It doesn't have value semantics. It is an object type. It is immobile, yes. And we're going to have this polymorphic allocator. Here, way down at the bottom, we have std vector of int, comma, polymorphic allocator of int. This vector will now contain inside itself a copy of the allocator, a polymorphic allocator instance. That polymorphic allocator instance is basically just a pointer to the address of this trivial resource. So what is the integer argument of the size n here? Oh, that is a typo, but you could imagine it was the size of data, for example. Yeah. So here's a summary of the two kinds, right? We had struct bad 2 slides ago, and now we have something very similar looking. We've just changed its name. But struct bad was object-like, right? It contained its own mutable state, and that made it a bad allocator. The source of memory was stored directly in the object. Allocate and deallocate, this is interesting. Allocate and deallocate were non-const because they had to mutate that state, right? When you called allocate on struct bad, it actually bumped up the used count and changed the values in data. And so this meant that it had to be non-const. With polymorphic allocator, allocating and deallocating using the allocator don't actually modify the value of the allocator, right? So they could actually be const. They aren't. Oops, but they could have been. With struct bad, moving and copying the allocator, as I said, is likely to leave you with a bunch of dangling pointer bugs. With polymorphic allocator, because it's just a handle, it is safe to copy. It's even trivially copyable, possibly. Am I going to get the meaning of equality between two allocators? At least implicitly, yes. The meaning is exactly what you would think. If an allocator is a handle to a memory resource, then equality means pointer equality. They point to the same resource.
It's important to splicing.
Yes.
That you don't need to actually pass the same object to everyone to start splicing.
Yes, we'll get to that later. Yes. We will get to something like that, yes. And lastly, this is the very last line of this is the one caveat. With struct bad, I mean, it didn't work. So good points don't really matter because it doesn't work, but there was no shared state, right? It was all contained within the allocator itself. and then you copied it to dangling pointers and it didn't work, so don't do it. But in the case of polymorphic allocator, it does not own the memory resource. It just points to the memory resource. And so you have to think a little bit about who does own the memory resource. What is its lifetime? What is the lifetime of that heap that I'm pointing to? So this clarifies our thinking about allocators. Even if you're not using C++17, and especially even if you're not using PMR or polymorphic allocator, because you may not, you can still take these lessons and use them to clarify your own thinking about allocators. The old style thinking, you might have said, an allocator object represents a source of memory. An allocator is the source of memory for things. This is not true, right? Don't think that way. It is not itself the source of memory. It is a handle to a source of memory, plus some other orthogonal pieces, which we'll talk about. And the source of memory itself is somewhere outside of the user of the allocator, somewhere outside the container. Here we can have, we have a program that maybe has multiple memory resources going on, multiple heaps going at once. It has multiple allocators. Some allocators point to a heap and uniquely point to it. Others share the same heap, which means you might have to think about thread safety with respect to can multiple allocators allocate from the same heap. Some allocators belong to containers, some don't. You can use an allocator without a container. If you have some sort of generic algorithm that would like to get memory from somewhere, you can pass in an allocator to it maybe. So this clarifies our thinking. However, now that I've told you all about these allocators that are handles to heaps, you might be thinking, what about stateless allocators? What about std allocator? Std allocator is an empty class. How could it possibly be a handle to anything? It doesn't have any bits in it. Well, mathematics time. And a stateless allocator is a handle to a source of memory, plus some orthogonal pieces, where the source of memory is a global singleton. For example, the new delete heap is a global singleton. There is only one possible thing that std allocator could possibly ever point to, and that is the global heap. So how many bits of object representation do we need to represent exactly one thing? Well, we need log of 1, which is 0 bits.
Well, if it can find the pointer to the global heap somewhere.
Doesn't need a pointer. Let's look at code. Let's clarify this with some code. So this is a little bit of a digression, but we will circle back around to that idea of the log of 1. But first, here's memory resource. This is the actual memory resource as it appears in C++17 with some namespaces around it, and I've removed some random no except and whatnot. But memory resource is a base class, and it is polymorphic. It has virtual methods. However, other than the destructor, which is of course public, all of its virtual methods are private, and they all begin with that do underscore. So do allocate, do deallocate, do is equal. And these are all private. They have public entry points, which don't have the do, right? So when you want to allocate something with a memory resource, you're going to call the public allocate function. It's going to dispatch down to it's going to do the virtual dispatch and call do allocate for you. This ensures that you can never have a derived class and say, you know what, I'm going to just skip straight to the code that I know this class has. I'm going to say, my derived : do allocate. That's private, so specifically, so you can't do that. And I kind of like this. The other thing that this means is that when I derive from it, as I'm going to do on the next slide, here's the actual new delete resource from the standard. Modulated, this is an implementation detail, what I'm showing you. What's standard is this function down here called new delete resource, and it returns a pointer to a memory resource that's just a static singleton. All right, I have this one instance. And this name, this singleton new delete resource, this is a made-up name that I made up. Somewhere off in the private implementation in the CPP file, it's going to say singleton new delete resource inherits from memory resource publicly, so everyone knows it's a memory resource, and it overrides the 3 member functions, which are private. So this is kind of cool because I don't have to put public up here or anything. I can just open the class and then override the 3 things, and I'm done. I never have to mention access specifiers anywhere. So I kind of like this pattern for that reason. So we override them to just call operator new and operator delete. For is equal, we'll just say, what are we saying here? If it is in fact this object, then it's equal, because there is only one object of this type, right? This instance down here. Does anyone have any questions about memory resource specifically before I go on?
Is this the place where old allocators before C++11 hook up, or is it done somewhere else?
Is this the place where old allocators before 11 would hook up?
Where there's no concept of having something that functions like placement new because
no.
Where the template does that about issues those things. You don't do it yourself.
The container is the thing that is going to have the allocator within itself, polymorphic allocator within itself. The polymorphic allocator is going to call the public allocate function on the base class. That's going to do the virtual dispatch and eventually get to our code.
Standard allocator traits. You call like
Allocator traits. We'll come back to that.
Oh, okay.
All right.
It is hooked up there.
Yeah. Thank you. So this is now polymorphic allocator. Oh, one more.
Do we lose the capability to do EBO with polymorphic?
Can we do EBO, the empty base optimization, with polymorphic allocator? Essentially, yes, because it's not empty. Right? Yeah, but you don't lose any space to padding because there's no padding. It's not empty. Yeah.
I think is it the case that with the polymorphic allocator you don't input an allocator, right?
Yeah. Let me go to this next slide, which has the polymorphic allocator on it. But yes, if you're using polymorphic allocator, you yourself never need to implement an allocator type. You use polymorphic allocator, which is a handle to a memory resource, and you yourself implement a memory resource, which is derived from standard PMR memory resource. Yes. Right. It could still inherit from it, but it wouldn't get any space savings out of doing that, and so it probably wouldn't. So here's polymorphic allocator. As promised, it has a pointer to a memory resource. And what else has it got? It has a constructor that can construct from the memory resource star. It has this rebinding constructor that we'll come back to. It has a default constructor that calls this global thread safe get default resource function. I'm not a huge fan of this, but just know that you can default construct a polymorphic allocator and it will go grab whatever your default resource is, which is usually the default new delete heap, new delete resource. There's a way to turn it back into a memory resource star by calling resource, and it has the allocate and deallocate functions that every allocator needs. It also has this other function that we'll come back to. And lastly, it has operator equal equal, and of course it also has an operator not equal, where you can, again, an allocator is a value type, so you need to be able to copy it, and you need to be able to compare copies for equality. Here we're comparing them for equality by just saying if they point to the same resource, they are equal. Or more specifically, we're going to delegate that to the resource. So we're going to ask the resource, are you equal to this other resource? In general, that will mean address equality. Did we lose the capacity to create a fixed capacity vector? Essentially, yes, but my argument is that you don't want to do that, or at least you don't want to try to abuse the allocator model to do that, right? A fixed capacity vector is a super useful type, but you should make it its own type. And once you do, you realize the memory always comes from within the object itself, and you don't need an allocator at all. You know where the memory is. There's no question.
Small size optimization vector. It's some fixed capacity, but it can grow beyond it.
A size optimization where it has some fixed capacity but could grow beyond that. Again, I would tend to argue, if you're doing like a small string optimization, for example, well, you could think about, well, how do existing standard library vendors do small string optimization with std string? How do they do it with std any, with std function? They don't abuse allocators to do it, right? They have their own ways of doing it, and you should copy those, not try to innovate with allocators, because it's not going to work. It's going to be bad. Okay, so this is polymorphic allocator, and it contains a 64-bit memory resource star, and therefore, as the purple box says in the upper right corner, the stateful allocator of size 64 bits can point to any of 2 to the 64th different memory resources. Yeah?
Can piece together a fixed size vector with like a non-joint buffer resource saying
Can you do crazy hacks? Yes, but don't. Now I'm going to change it a little bit. I had a 64-bit quantity there that could point to any of 2 to the 64th different things, right? Now I'm going to do, again, this is a crazy hack you shouldn't do, but in principle, it's less crazy than anything we were just discussing about fixed capacity vector. This is a 1-byte allocator. It's an allocator, which is a handle to a memory resource, but it only takes up 8 bits. And we're actually going to use those 8 bits as an index into this atomic ref counted. I'm not showing any of that code, but I did it in practice, and the link is not here. So you can't prove me wrong. I totally did it. We've got this table of 256 different memory resource pointers, and we're going to update it. And as we make copies, we're going to ref count the things, and we're going to find an empty index when we need to. And we can then point to any of 256 different memory resources at a time. If our program has fewer than 256 different memory resources, we can get away with using 1 byte to represent the address of any of them. So that's very cool. OK, now suppose we only have 1 memory resource in our program. Then we know where it is, and we don't need any bits. And then we have this 0-byte allocator with 0 bits, and it can represent any of 1 different memory resource, which happens to be, in this case, new delete resource, because we chose that. We could choose something else, too. It would be a different type, right? No, different behavior. Right. Cool. That is essentially std allocator. Question? In the previous one, where were we setting the index? We were doing that in our, in that comment. That comment, totally, the compiler will just do the right thing, right? And you can see here when we do the copy, we hide it all away in this incref function, and again in the decref function. So, yeah. Well, I heard this morning we can just use contracts, and it will just solve everything. So. Compilers will be able to parse those, no problem. Corollaries to the new way of thinking. Again, just to rehash. You're all in this room to learn that allocator types are just like pointers. They're handles to memory resources, and therefore they should be copyable just like pointers. This was always true, even pre-11, even pre-17. This was always true, but now it's more obvious. Not only should they be copyable, they should be cheaply copyable. Not necessarily trivially, but you're going to be copying allocators a lot. The container is going to be copying them behind your back. We'll see that in a minute. And memory resource types, contrary-wise, they're going to sit in one place and be object-like and generally immobile. They're going to have their state mutated by means of these allocators. Memory resource, for example, might sit in one place and have a buffer inside itself and allocate chunks out of that buffer as needed. So allocators need to do as the pointers do in one more very subtle way that I did not know a year and a half ago. Notice that in our 1-byte allocator, I gave it a copy constructor and I did not give it a move constructor. Even though it's doing this sort of ref counting thing, you'd think, oh, well, it would be super fast to just copy it over, zero the thing out, just like shared footer does, right? Have it be efficiently movable. It is not efficiently movable, and the reason for this is that allocators should be essentially copy-only types. When you move out of an allocator, the thing that's left behind in the source object, the moved from object, must preserve its value. This is very weird because we are used to not thinking like this when we're talking about move semantics. However, this is extremely important to have because down at the bottom here I have v1 and v2, and they both use some sort of custom allocator with some state, and I move out of v1, and I move everything out of v1, including the allocator. I've moved out of the allocator, and now v1 is in this unspecified but valid state. Do you define equals delete? No, you don't. You define equals to the copy constructor. Right? So I've moved out of the vector. Now the vector must be in an unspecified but valid state. The allocator, in practice, will be in a moved from state. But if I then clear the vector and start pushing things back in again, that doesn't magically give me my allocator back. Right? I don't know how to get an allocator, so I better hang on to the one I had. That means that when I move out of an allocator, it better still have the same value and still be usable, because someone's going to try to push back in the vector again. Bryce? Is this postcondition completely unique in the standard library? Other than for trivial types, yes. But for example, for a pointer, if I move out of a pointer, it preserves its value. You know, if I move out of an empty class, it preserves its value, such as it is.
So you could say that this is some sort of a trivial, but trivially in a different sense.
Yeah, it doesn't need to be literally trivial, but it needs to do the thing it says on the slide. So just be aware if you're implementing an allocator and it needs to do some weird ref counting type of thing, you know, watch out for, don't get too clever with it. Really just give it a copy constructor. But again, you shouldn't really be implementing your own allocator type too often because you're going to be using polymorphic allocator or standard. Well, but if you need an allocator that's not polymorphic allocator and not standard allocator, you're going to have to implement it yourself because those are the only two standard allocators. It is legal to use moved from containers. You don't know what state they're in, but they're in some kind of state where you can, you know, you call anything without a precondition. In this case, clear, right? People say all kinds of things. This isn't that talk. Go to one of Howard's talks. He'll love it.
What would happen if I just took the headers from C++ 17 and put them in C++ 11 program with polymorphic allocator? Let's set it as a typical allocator for a C++ 11 vector.
Could I use polymorphic allocator in C++ 11? Yes, absolutely. There's nothing that needs C++ 17 or even 14
Without changing the vector, which is in the
without changing vector. Yeah, correct. If you take it literally from something like libc++, you will find out that there are error directives in the file that prevent you from doing this. But except for the nanny state, yes. Okay, so we're not allowed to move allocators more cheaply than a copy because basically we have to copy. Except, I should say, the source object has to preserve its value. If it does have other crap associated with it that's not part of its value, like a cache of some, like I don't really know what, but if it has some non-essential state, maybe that non-essential state will be moved over. That's okay. Non-essential state will be moved over. And the essential state will be copied. And I was thinking about this right after my last talk because it was brought to my attention. And it's interesting that C++ has this notion of copy and then move, where move typically means steal all the guts from the other thing, right? From the R value, you can steal all the guts. And copy means don't steal any of the guts. But with allocators, that's a little bit changed, where copy means don't steal anything. Move means you can steal the inessential stuff, but you need to leave enough for it to survive on its own. Like steal one of the kidneys, but not the other, or something like that. And we don't, for allocators, we don't have an idiom or a way to tell the library, hey, I want to steal the whole thing. Destructive move might be something like that. And you'll notice on my name tag here, it says trivially relocatable, so ask me about that. But in general, there's many different kinds of stealings that we might want to do, and allocators have a different set of two kinds of stealings they can do than other types.
I learned about 2 minutes ago in your single byte allocator.
My single byte allocator.
Will the compiler just call the copy operator when there's a move that needs to be done, or are we overriding the move here and doing ourselves?
Here in particular, I don't give it a move constructor, and therefore it will copy, because the copy constructor exists and the move doesn't. Yes. However, if I had given it a move constructor, then it would call the move constructor. Yeah. When I move the vector, it will attempt to move the allocator. It will not fall back onto copy, even though. Yeah. Moving on. All right. So why do containers copy allocators in the first place? Because of something called rebinding. Allocators are rebindable family types. So the type to allocate, for unfortunate historical reasons, is baked into the allocator type. If I want to allocate integers, I need to use a std allocator of int, or an allocator of int. And when I say allocate to, that means two somethings, and because it's an allocator of int, it means two ints. This works great for std vector, because I quite often need, with std vector, to allocate a contiguous sequence of 2 ints or 5 ints or whatever. This only works for std vector. It does not help anybody else in the world, right? Because std list doesn't even want to allocate t to begin with. It wants to allocate node of t, which is a t with a couple of pointers. Std map of takes this allocator of pair const k v. It doesn't want to allocate that type at all, right? It will never allocate an object of that type. It wants to allocate rb tree node whatever. So we need a way of taking the allocator that we got, which is associated with one particular t that we almost certainly do not care about, and rebind it to the t that we do care about. And so we have these family of related types, alloc of int, alloc of double, alloc of void star, etc. An allocator value, which is representable in one of these types, must be representable in all of the types. Any type that I want to allocate, I should be able to, step one, get that new type, alloc of some type, and then I should be able to take the value that I have and convert it in some way, preserving its value, convert it to this other type. How do we express a value-preserving conversion in C++? Cast, static cast, right. So, so rebinding is useful when we have this foo, or possibly a foo of u, and we need to get a foo of t. So there are basically two ways to do it. The STL prefers this rebinding strategy, where we have this function, or we have this class called, class template called allocator traits, standard allocator traits. We specialize it for our type, or we use the default specialization. Normally you don't have to mess with it. You shouldn't mess with it. And it has this member type def rebind alloc of u. U is the type that we want. The alternative is we could do something like this, where we take a template parameter, and then we can just instantiate it, just substitute in u. This is not used in the STL, not even for stack and queue, for those of you thinking about those, no. So generally know what rebinding is and how to use that. Bryce, I'm going to stop taking questions from you. You should have asked all these in Aspen. That is true, and I thought I had a slide on that. Maybe I got rid of it. But yes, template class ... is quite possibly what you want there, because otherwise it's not going to work for some things. Yeah.
The reason we have this type though is because we want to ideally know how much size we have, how many bytes to allocate for that type. Why doesn't the allocator just deal in size of?
Why doesn't the allocator just deal in bytes? Memory resources do deal in bytes. They deal in, but they also deal not only in bytes for size, also alignment, which the original, going back to C++ 03, they didn't have to worry about alignment because you got the t, you just use whatever the alignment of the t was, right? And there may possibly be other things you might want to consider, such as, we'll see the construction is piped through there, but that doesn't really matter. But what pointer type do you return? Do you just return void star? No, you'd be type safe and return t star. So then you have to know what t is. So allocators are rebindable family types. There are many other kinds of rebindable families in C++. Allocator types are one example, which we just saw, but also pointer types. For example, t star. I can take a t star and I can use pointer traits to rebind it to u star, and I can static cast between t star and u star. Or if I have fancy pointers such as boost, offset pointer, and so on, then I can use pointer traits as well to cast between those. And smart pointer types, unfortunately, there is no smart pointer traits, but you can still convert or rebind a smart pointer like a shared putter of int. I say I have a shared putter of int, but I would really like a shared putter of double. How do I get from where I am to that? I can use reinterpret pointer cast. And the idea is that we have a generic way of doing this, so that you can do it with std shared putter, you can do it with boost shared putter, you can do it with weak putter, you can use it with your own types. That these are all rebindable families. Right, I'm going to move on. Each rebindable family has a prototype or representative of the equivalence class. For example, there's a void pointer type in pointer and smart pointer families. Allocator families also have a proto-allocator type, except the asterisk is that they don't really, but they will as soon as either executors or networking gets into the standard. Then we will have this proto-allocator concept. Or I can say alloc of void. Now, alloc of void here, if alloc is an allocator, then this is not really an allocator, right? Because it couldn't possibly do allocate. I can't say allocate 2 voids, please. Deallocate 2 voids. That's not going to work. But what I can do is I can use this to communicate a value, right? Because an allocator is a value type. I communicate which memory resource I would like to use, please, through one of these alloc of void. The person on the other end, the container or whoever, can rebind that type using allocator traits, say rebind alloc to int or whatever they need, and then cast the value. And now they have an allocator with the appropriate type and the appropriate value. Yes, it has all the same state as an alloc of int or an alloc of double, but it just has a sort of curtailed interface. So yes, and if you're designing your own thing, where you don't have to be constrained by the history of C++, please do use this sort of proto-allocator or representative concept. Please don't use alloc of std byte. Don't do that. Or alloc of char, or alloc of int star star star. Right. So if we were designing the STL today, in fact, we'd use the proto-allocator type in our interfaces to save on instantiations, right? Rather than making up all of these different alloc of int, and in the case of vector. In the case of list, we have alloc of int, but it's secretly going to rebind it to alloc of node. For map, we have to make up alloc of pair of constant int, and then it's going to rebind it to node. We're making all of these different instantiations that most of them never get used. It would be better to just have one proto-allocator and then have list and map make the ones that they're going to use. And we never try to make the intermediate ones, like pair, constant, int, that's never going to get used.
Why would the drier version move the template type parameter onto the member functions? Why would it just be allocator of those and then make, say, constructor allocate
Let me see if I understand that. In fact, are you saying, are we circling back around to memory resource star? Yeah, could we just say, why don't I just pass in a pointer to a memory resource or something like that?
I'm not asking that because the presence of the virtual table means you can't template the member functions of every resource and have that work with templates and do the double volume. But if you just had, if allocator was a class rather than a class template that had a bunch of template member functions rather than non-template member functions.
Yes, I see.
Then you would only need one type and then have a whole bunch of template members.
Yes, why don't I just have one class type with many member function templates rather than a class template with member functions? I suspect that the historical answer has to do with poor support for member function templates in the 90s. I don't know. But yeah, it does seem better. Yeah. With the proto-allocator type, the container must rebind its allocator before any operation, so it would look something like that. Why don't we just get rid of all this rebinding entirely and just go with memory resource star? Well, the reason is that an allocator is not merely a pointer to a memory resource. It's a whole bunch of other stuff too, and I have 18 minutes to tell you what that stuff is. An allocator is more than the source of memory. So when I do an allocation like this is the almost the correct way to do an allocation, except that I have lied in that here this needs to be a non-const L value, so the result of a static cast is not going to cut it. And that's because the allocate member function is not const, which it should have been in the first place. Here, the result of allocate is going to be of type allocator traits of alloc_t : pointer, which is typically just t star, but it could be something fancier, such as an offset pointer or some other very fancy pointer type. And that means it's completely up to the allocator to decide how its pointers are represented. Again, typically they will just be t star. But if you wanted to say, I'm allocating out of GPU memory or shared memory or some weird thing where the associative array memory where the format of a pointer needs to be represented in memory in some very specific way, this is where you could hook in to do that with the pointer member type def. The container is going to use that pointer type def for all of its pointers. Problem is, its pointers is really vague. Who made this pointer? Container uses pointer for all allocations. So here's std list. We have a node as promised, and we have all these pointers running around, right? And we have this heap here. And the idea is that any pointer that points to something on the heap had better be colored red. So the first interesting thing to note is that we have two pointers here that are stored outside of our heap, as I've drawn it here. This list object is presumably on the stack or something, and all of its allocations are taking place in the red heap. But that means it needs to have two red pointers pointing to things on the heap that are not themselves stored on the heap. So that's a little weird. I need whatever my red pointer type is, my pointer type def here, it needs to be able to represent, or it needs to be able to be stored outside the heap if this is going to work. And then also, these two pointers, the green ones, are stored inside the heap, but actually, because of the sentinel node stored within the list object itself, they point to places outside the heap. So, but they have to be the same type, right? mprev here, this is a red pointer pointing to something on the heap. This is pointing to something outside the heap. They need to be the same type, right? Because they're both the same field. And so this is very strange, right? I have red pointers that live outside the heap. I have green pointers that live in the heap. And so this essentially means that fancy pointers, whatever fancy pointer type I pick, needs to have the same range as a raw pointer. So I need to be able to take one of these fancy pointer mnexts and turn it into a reference to this node by dereferencing it. And of course, if I can do that, then I can take its address, and then I have a raw pointer. And vice versa, if I have a raw pointer to this minternal node, I need to be able to get that as a fancy pointer. So fancy pointers and native pointers must be interconvertible, have the same range of values. Does this mean that they are exactly the same and there is no reason to ever use fancy pointers for anything? Honestly, if you walked out of here thinking that, I wouldn't complain too much. But I have two reasons the answer is no, and this is also covered, by the way, in my committee paper from about a year ago, P0773, toward meaningful fancy pointers. So if you wanted to go read that, that would be cool. So are they the same type? No. Because just because they have the same range of values, remember all the way back to the beginning where we had A as an int and B as a long, and they were both value 42, but they had different in-memory representations. So the type also involves object representation. For example, boost offset putter is part of the boost interprocess library. It has the exact same range. It can address any of memory, but it does so with a different bit pattern than a native pointer would. Bob Stiegel has a thing called synthetic pointers. He gave a couple of talks last year and also at C++ Now and also I think this year. He calls them synthetic pointers. Again, same range as native pointer, but different memory representation, different behavior at runtime, different performance behavior, I should say. And the other reason is, besides object representation, is that the fancy type might be augmented with extra data. So it might actually be bigger, fatter. It might have metadata that's used by the deallocator, for example, so that it could carry information about where the allocation came from to enable the deallocator to work faster. Something like, this came from slab 5, so the deallocator can look it up very quickly. It might carry something like affinity for GPU memory. It might carry array bounds. I call these fat pointers, so that the metadata is not used necessarily when deallocating, but it's used when doing pointer arithmetic and when dereferencing. These cases are supported only inconsistently and possibly accidentally by vendors, so be very pessimistic if you're going to try to use this kind of thing. But I do think that it would be nice if more vendors supported this kind of thing, and if the standard explicitly said, this is why we have the pointer type def, is so you can do this kind of thing. Because if you're limited to only use native pointers, why did we bother making all of this machinery?
Given the construct on the allocator case works in terms of raw pointers, can the fancy pointers provide us any measure of type sync?
Can fancy pointers provide us any measure of type safety given that allocator traits construct takes a raw pointer? Allocator construct should take a raw pointer because it doesn't actually care about the pointer type, it just needs an address. And as we've said, they have to have the same range, they have to be interconvertible.
Doesn't that imply a necessity for implicit conversion?
For implicit conversion, no. The conversion, when the container takes its fancy pointer and passes it to construct, it needs to do the explicit conversion, the explicit cast with static cast or something like that, because the fancy pointer might not support implicit conversion. Yeah. In fact, you ask the people who are actually getting their papers approved, and they will say it shouldn't even use static cast. It should use like std : pointer to, or possibly address of, or to address, but static cast is the right answer, right? If I have the same value in two different types, how do I get from one to the other? I do a static cast. So a C++ allocator is a runtime source of memory, handled to a memory resource, and it decides the pointer type. So it's a runtime source of memory, and it also decides the pointer type. Also, we haven't really talked about this, but it decides whether the source of memory should move with the container value or stick with the container object, whether this container that I'm building, this instantiation or specialization of std vector, am I going to be using it primarily as a value type, or I'm going to be moving it around a lot, returning it from functions, and I'd really like it to move very efficiently? Or am I going to be doing using like the move assignment operator, but if I have one heap over here associated each with a vector, and I say I want to copy this vector into there, does that mean that I want this vector to get a pointer into that heap? Or does it mean that I want to copy all the data elements over into this heap? I call this the stickiness of the allocator, and you can control that via these traits. And lastly, it's a runtime decider of how containers sub-objects should be constructed through the allocator traits construct, so that you can have a vector of vectors of things, and it can pass down an allocator all the way down to say, by the way, my elements should, even if you're emplacing some other thing, I really also want to add an allocator onto the back of that so that all of my sub-objects will come in out of the same heap. So it's a handle to a heap plus some orthogonal pieces. We might separate some of these pieces. There are only these two allocators in the standard, but you can make up allocator adapters or things like that. You could take a non-sticky allocator adapter that took in some kind of allocator type and put out an allocator type that was almost the same but just had different stickiness. Or one that took in some kind of allocator, maybe a handle to some sort of heap, and then said, I want a bounds-checked allocator that will return fat pointers instead of native pointers. And I don't want to change where the source of memory comes from. I just want to change the kind of fancy pointer that's getting returned. 8 minutes. We're doing all right. We're going to switch gears. We're going to go even more speculative here. Fun. How are analogous handle types handled in other areas of C++? So I've been talking about how an allocator is a handle to a memory resource, and how this clarifies our thinking about how to deal with allocators, particularly in relation to containers. Can we take that intuition and apply it to anything else in C++ today? Well, an allocator is a cheaply copyable handle to a memory resource. An iterator works very similarly, not quite the same, but an iterator is a cheaply copyable handle to a thing, essentially a memory address, but represented maybe a little bit differently, to a container's contents, plus some other bits, some orthogonal bits like iteration direction or a value category. For reverse iterator is like a handle to a container's contents, but also goes the other direction, right? And move iterator is a handle to a container's contents, but when you dereference it, it's going to move out of it. And incidentally, I promised to talk about the difference between facades and adapters. I think of it this way, which I think is how Boost thinks of it. If there is any system at all, it is this. A facade is providing the complete set of operations, the complete, I want to just say facade again, but that won't help. So the complete set of operations, the standard zoo of all the operators. So for example, I could just implement the primitive functions, next and dereference, and then from that it would generate prefix plus plus and postfix plus plus and minus minus and prefix minus minus and star and arrow and just get all of those right, and I would only have to do maybe 5 different primitive operations. And then I just ask the facade to generate the rest in terms of my primitive operations. An adapter, I pass in some existing complete iterator type that already has the whole zoo of operations, and I just say I would like these certain operations to behave differently. For example, standard reverse iterator is an adapter in that sense, and it says, do everything that this guy does, but just change the order of plus plus and minus minus. So that is an adapter. What else are we going here? We're getting close to the end. Oh yeah, executors. Coming soon. In fact, I think they just had a meeting about this. There's executors are essentially cheaply copyable handles to execution contexts, possibly coming in C++ 20, 23. Executors light in 2020. Okay. So the executors proposal is saying that an execution context is a program object. They're using specifically the term object because it connotes object type. It's going to live in one place and be basically immobile, and it's going to represent, in some sense, like a thread pool, something like that. And then if you want to use the execution context, you don't use it directly, just like you don't use a memory resource directly. You wrap up a handle to it in something called an executor, and you pass that around to things that need to get threads. Executors are to execution what allocators are to allocation, yes. I agree with that. But only if you think, as I think, about what are allocators to allocation anyway, right? An allocator is a handle to a heap. Now the interesting thing about std executor is that it's actually type erased just like std function. I believe that's still the plan. So you can put any kind of capital E executor, anything that satisfies that concept, into a std executor. This is not true of polymorphic allocator. Polymorphic allocator says polymorphic right in the name, but it doesn't do runtime polymorphism in the way we've learned to expect from std function and std any. We've been spoiled. It's talking about old school classical polymorphism, where you must inherit from std PMR memory resource in order to have a polymorphic allocator point thing. We could actually imagine a truly polymorphic, runtime polymorphic allocator that would look something like this. Resource adapter here, that's something you can write yourself. It was somehow omitted from C++ 17, but I think it might be coming, who knows. But it's something that can take any old allocator and wrap it up in something derived from memory resource. And so then you have a path to take your existing allocators, turn them into memory resources, and then have polymorphic allocators coming out the other end. So if that sounds useful, that is totally possible, as long as you have some way of learning about or thinking about the lifetime of that shared state. Who owns that resource adapter? Who owns that memory resource? Right, that was the trade-off from that table earlier. And so here I'm just wrapping it up in a shared footer the way we're used to. With that, questions, because we got about 2 minutes left. Yeah, use the mic if you can.
So I think I understood it, but I may have missed something. One of the most, the most popular use cases for allocators in C++ is to have bin memory resources, like have for 8 bytes, for 16 bytes, whatever.
Yeah,
and then
pool resources.
Pool, okay, but bound to a certain size in order to deal with fragmentation. Right. So this, as far as I can see, doesn't help me at all with it. And in fact, it even makes it worse for the cases of list or map because I don't even have access to the internal like structure and its size.
You don't know what bin sizes to use because
so and it makes it worse because I need to provide the memory resource, but I don't know which memory resource to provide, and it hides away the type before this. Back in the old school, I could say I could have global memory resources, and then in the allocators constructor, I could choose based on the size from the global list of pools of different sizes.
Right.
So
yeah, so I think I understand the question. And I would say just think more compositionally in that this pool resource, the reason I said we call that pool resource was because in the standard in 17, they actually do call it. There's a synchronized pool resource and an unsynchronized pool resource. And those are slab allocators of the type that you're used to with buckets of different sizes. And the idea is that that entire thing is one memory resource. Yeah, and then when you ask it for n bytes, it dispatches to figure out which pool to get it from and goes to that pool.
Okay.
It's not very configurable. There are basically no knobs on the standard one. I wouldn't recommend using the standard one. But again, it really clarifies our thinking and gives you a blueprint for if you're going to implement that kind of thing using memory resource. Just go look at the libc++ implementation and you know, copy
the memory resource needs to provide all the types of bins with it. I cannot have a memory resource for a single type of bins.
A pool resource needs to provide all of those different bins. But you could have another resource. There's one called monotonic buffer resource that's just a huge chunk of memory, and it just allocates out of it, like the trivial resource we saw at the beginning. And it doesn't care how much you ask for. It's just going to give you that much, and it just doesn't even care, right? So it doesn't need to know about different bucket sizes and all that. It's just very, very simple, and you can go in between, you know, different strategies. But they're all expressible in this memory resource model.
Hi, slide 16. Is there a reason why it's using a pointer and not a reference?
Is there a reason to use a pointer and not a reference? Good question. I would say yes, stylistically. We are not passing in a memory resource. We're passing in a pointer to a memory resource. Right? If we took a reference is, stylistically, it looks like we're passing in the memory resource, and that the fact that we're taking a reference is sort of an optimization. But here, no, we really care about the address of that resource. We need that address to be the salient thing that we're going to keep. We're going to keep a pointer to it. And you need to know when you're calling this constructor that the address matters. You know, you don't pass us a temporary, don't pass us something and then later move out of it. Like, give us an address of a thing and we're going to remember that address and use it later. Does that make sense?
Okay, fair enough.
Yeah.
It's a stylistic decision, though.
Yes. It can't be null, right?
That's exactly my point. That if you want to make sure it's not null, then make it a reference. And
if you want to make sure it's not null, then make it a not null T-star. Yeah, don't misuse references as non-null pointers. Yeah.
Thank you.
Cool. We're into break. Thank you all.